Okay, we're going to be starting chapter 11 here today. We've learned a lot in the last several chapters about different types of significance tests, confidence intervals. Anytime we have talked about significance tests or confidence intervals, it's always revolved around either running a, say, significance test on a claim that was made about a proportion of a population, or a claim that was made about a mean of a population. And we're going to kind of go in a different direction here today. We're not going to be looking necessarily at proportions or means. Those are always quantitative in nature. We're going to be looking at how do you run significance tests when what it is that you're measuring is maybe more categorical in nature. Okay, and a lot of times we can use proportions to reference categorical variables, but we're going to be studying in this chapter 3 different types of significance tests. They each have a unique name, but they all revolve around the chi-square test, okay, which is just a Greek letter of the alphabet here. So we're going to start in this section exclusively with the name of the test is called a chi-square test for goodness of fit. And I'm just going to begin here with kind of emphasizing when you would use this particular test. You would use this when you are sampling from one population and you are trying to measure from just a single population one categorical variable across several categories. And you'll see what I mean here in just a moment. An example of that might be, let's say your population is M&Ms. Okay, and the categorical variable is the color of the M&M. You'll notice there are several colors of M&Ms. Okay, so that's what we mean when we're saying one categorical variable, that would be the color, but there are several categories of colors of M&Ms. The chi-square test for goodness of fit, what you're doing is you are comparing the observed distribution of a categorical data to a hypothesized distribution. We know that when we run significance tests, there are always hypotheses. A null hypothesis is the claim that's made, and then we're searching if the evidence that we get from our sample shows that it's in favor of the alternative hypothesis. Now, what I want to make sure that we're noting here is that we calculate the chi-square test statistic. This is how the chi-square variable is measured. Kind of looks like almost a cursive x squared. We are always going to be calculating that, or it's always calculated using the counts. And again, I'll demonstrate what I mean by that. But when we see this observed minus expected squared divided by expected, that is talking about the counts. How many of those things are you expecting to see in your sample? And how many of those things did you actually observe from your sample? And you'll notice here, this formula is on the formula sheet. Okay, so let's take a look at an example here. Mars Incorporated is the company who owns the company who makes the M&M candies, and this is a legitimate claim that they make. They report that their regular milk chocolate M&M candies are distributed, the colors are distributed on average in this fashion. 13% of them are brown, 13 red, etc. You can see these different percentages is what they're claiming the distribution of the categorical variable color is across all of these different categories of colors. Okay, now, we could conduct a hypothesis test to compare the sample proportion of just one color to the hypothesized portion of that particular color that you see here. But we would only be able to test one color at a time. And so that would limit us to running a one sample z-test for the proportion of that one color. But if we wanted to take one sample and say we wanted to test the proportions of each color at a, say, 5% significance level, we would have to run 6 different one sample z-tests. On the calculator, it's called a one prop z-test. We have to do 6 different ones of those because we have 6 different categories of colors. So what we're going to do is we're going to develop a more appropriate way to kind of fix this issue of having to do 6 separate significance tests. This new procedure is not going to use a z-curve or a t-curve. We know that the t-scores are reserved for means. Instead, what we're going to be doing is we're going to be comparing the expected counts in a situation to what the observed counts are, okay, rather than comparing the proportions. And so I want you to take a close look at what we have here in this box. This is how, for the chi-square goodness of fit test, this is how your null hypothesis and your alternative hypothesis would be worded. Okay, the null hypothesis is essentially saying that the stated distribution of your categorical variable in whatever the population is that you're talking about is correct. Okay, now I know this is written very generically. If we were to do that for this particular problem up here, okay, we could say something like the stated distribution of the colors of M&Ms is correct. And correct would mean that it's what Mars Incorporated is claiming. Okay? And then the alternative hypothesis is basically saying, hey, that stated distribution of the color across the M&Ms, it's not correct. So in other words, it's not these percentages that are being claimed. Okay? Another way of saying it is to say the true distribution of the population matches what they're claiming it should be, and the alternative is that the true distribution of the population, it does not match what is claimed. Okay. Now, there is degrees of freedom for this. The degrees of freedom is always the number of categories minus 1. Okay, you'll notice that we're using a K here to represent the number of categories. This is not the sample size minus 1. It's the number of categories. So in this example, the number of categories is that there are 6 different colors. So in this example, we would be using 6 minus 1, or 5 degrees of freedom. A couple things that I just want to highlight or mention to you here is please note that the chi-squared test statistic deals with counts, not proportions. You'll see why this is in a moment, but the chi-squared test is always a one-tailed test to the right, okay? The alternative hypothesis is always essentially saying that the null hypothesis is not correct, okay? Larger values of your chi-squared test statistic is stronger evidence in favor of the alternative hypothesis, which would be saying that the stated distribution is not correct. And as I had just mentioned, the degrees of freedom is actually the number of categories minus 1, not the sample size minus 1. Okay, please note here that what the chi-squared test statistic tells you is it tells you by how much what you're observing is deviating from what is expected. So that's why we're saying if that chi-squared number is large, then what you are observing is really deviating from what you were expecting to observe. And that means that we're saying, look, what we got in our sample is much, much different than what we were expecting to see based on your claim. That's providing stronger evidence in favor of the alternative, which is saying that null hypothesis, that claim, is not true. Okay, so before we jump into just 2 examples here today, I want us to just take a look at the chi-square distribution. Okay, something that you should note is that this distribution, the chi-square distribution, it is always skewed to the right. Okay, a couple of things and reasons why that is the case here. I'm just going to mention just a few properties here. I'm going to try to highlight these here. Okay, one property, and you'll see that I have several different chi-square curves drawn here. Okay, I'm going to highlight one there in yellow. I'll go ahead and highlight this one here in green, and we will do this one here in blue. Okay, the mean of your chi-square distribution is always equivalent to the degrees of freedom. Okay, remember your degrees of freedom is the number of categories minus 1. Okay. Now, the mode which is where the peak would be of your distribution, is actually the degrees of freedom minus 2. Okay, you'll notice the distribution is always skewed to the right. And the reason that it is skewed to the right is it can only exist for positive values. And that is because you're squaring the differences. If you look up here at how you calculate the chi-squared test statistic, you're squaring the difference between observed minus expected. When you square something, then it can never be negative. It has to always be a positive value. So your chi-squared test statistic is always positive. That is causing it to be skewed to the right. The higher the degree of freedom, you'll notice the less skewed to the right it is. Okay, so the more categories you have, the less skewed to the right it would be. You can see here the degrees of freedom was 1, which means you would have had 2 categories, very skewed to the right. Okay, here degrees of freedom is 4, you would have had 5 categories, still very much skewed to the right. But then when we start getting into this blue curve here where the degrees of freedom is 8, there would have been 9 categories. You can tell it's less skewed to the right here. Okay, so let's talk through how to actually execute a chi-square goodness of fit test, and we're going to use the M&M example here. Okay, this is the claimed distribution here that you can see these 6 different percentages here. We're talking about Jerome. It says his class collected data from a random sample of 60 M&Ms. Important to note what his sample size is. Now you can see over here it says the observed counts are listed below. So the total in this column would be 60 M&Ms. You can see 9 of the 60 were blue, 8 were orange, etc. Okay. Now, you'll notice along the left side of your paper, you see a familiar acronym. Phantoms is typically what we use to help walk us through and make sure we don't miss any of the steps for doing a significance test. And that is what this is, the chi-square goodness of fit significance test. Now, the one thing that will not occur in this acronym is there is not a parameter that we are testing. We're not testing a proportion, we are not testing a mean, and so the P in phantoms, where we would normally list and define what our parameter is that we are testing, you will not do anything for that. So I have an X here. So we're going to start out, we're going to state the hypotheses for this chi-square goodness of fit test, which is what the H is set up for. Okay, H sub O would just be us saying that the company's claimed color distribution is correct. Okay, we can see what that is up above here in the problem. Okay, and then the alternative is basically that the company's claimed color distribution is not correct. Okay, we also want to list in this step what our significance level is for running this test. Remember, if they don't state one in the problem, we use our default alpha level of 0.05. Okay, the A in phantoms, we know that that always represented the assumptions, which was the conditions. We will learn this in the next example we will do. So I'm just going to write down here, we'll learn later. Okay, we'll talk about what those conditions are. We know that we always have to check those technically before moving forward with the significance test process, but we're going to skip that just for the moment here. Okay, it mentions here they want us to calculate the expected counts for each of these colors. So in other words, if you were going to take a sample of 60 M&Ms and you were told that, I guess we have blue as our first color up here, you were told that 24% of the M&Ms are blue, then how many of these 60 would you expect to be blue? Okay. Well, essentially what we would be doing is we would be multiplying 0.24 times 60. Now, you're going to get decimals here. Never round these expected counts. It's very, very important. Never round them. So 0.24 times 60 would be 14.4. We move down here to orange. The claim is that 20% are orange. Our sample size was 60. We should be multiplying 0.2 times 60. We would expect 12 of the 60 to be orange. Okay, so you kind of get the idea here. I move over here to green. 16%, I'm going to do 0.16 times 60. That's going to be 9.6. Yellow is 14%. 14% of 60 is 8.4. And both red and brown it says are 13%. 13% of 60 is 7.8. Okay, please make a note to yourself that do not round expected counts. Okay, do not round those. Okay, so we're moving on here. Part C says calculate the chi-square test statistic. Now, when you're calculating the chi-square test statistic, you're going to be using this formula right here. Oh, I guess if we're moving down through our acronym here, the N stands for to name the test. This is called the chi-square goodness of fit test. Okay, that brings us to the T, where we calculate the test statistic. Okay, this is using this formula here for chi-squared. So I'm going to set this up. Chi-squared equals, and in each scenario here, I've got 6 different colors. So I'm going to be doing my formula 6 times here. In the numerator, I'm going to be doing the observed, these are counts, not proportions. The observed count minus the expected squared divided by expected. So I'm just going to start with blue here. That would be 9 minus 14.4 squared divided by 14.4. Then I move over to orange. Observed minus expected. I square that. I divide by expected. Okay, again, this formula right here, it's on the formula sheet. Okay, so I'm going to write this out here for all 6 of these colors so that you have this written nicely for at least one example here in your notes, and you can kind of follow how we're getting the value that we're going to come up with for chi-squared. Okay, this is telling us what the difference is between observed and expected. This comes out to a chi-square value of 10.180. Okay. Now, essentially, here's what we're trying to do. We're saying we have this curve. We know that it's not normal. It is skewed to the right. The chi-squared value, I'm just going to mark, we're just going to say is right here. Okay, and what we're looking for is we need to obtain the p-value. The p-value is the shaded area to the right. Okay, this is always to the right here. Now, there is a chi-squared table that is provided for you on your formula sheet. I'm going to show you how to use this to help you get the p-value, and then I'll also show you a small feature on the calculator that can be used as well. Now, I did grab a small excerpt here from the calculator, or I'm sorry, from that table, but I'm going to reference this right here. Okay, this is table C. You provided this on the formula sheet. Let me show you how to use this. You'll notice as you look at the picture, you'll notice how it reminds you that we're talking about the chi-square test statistic. It is always skewed to the right. It is always a right-tailed. You're always shading to the right. The chi-squared value is your boundary marker here. We're looking for what that probability is. What you would do is you would follow the far left column, degrees of freedom. Okay, on this particular problem, the degrees of freedom is 5. There were 6 color categories. Degrees of freedom is always 1 less than that. Then what you're going to do is you're going to take the fact that we just calculated that the chi-square test statistic was 10.108. And you're going to look across this row and figure out what are the 2 numbers that 10.108 feels like it falls in between. Okay, falls in between. And whatever it falls in between, you're going to come up above here and you're going to find those 2 values here. Your p-value is some number between 0.10 and 0.05. It's a number that falls in between those 2 numbers. Now you can see if I go back to that excerpt that I had included here, you can see I shaded that 10.180 falls in between those. That means your p-value is some number between 0.1 and 0.05. We don't exactly know what the p-value is when you use the table, but we know where it's at in between there. Okay, my preference is to use this feature on the calculator. Just like there is a normal CDF feature, there is a chi-squared CDF feature. If you choose that feature, you're going to find it in the same menu that you would find normal CDF. You're going to press second and the VARS button that takes you to the distribution menu. On my calculator, it is option number 8. You're going to need 3 inputs, one for your lower bound, one for your upper bound, and they always want you to report the degrees of freedom anyhow. That's why it's nice just to use the calculator feature. Your lower bound will be the chi-square test statistic always, because that is going to be your left boundary. The upper bound should always be 10,000 because this is always a right-tailed test. And when you select that on the calculator and enter that data in, it should give you the exact p-value, which you'll notice is going to come out to 0.0703, which is definitely a number between 0.05 and 0.10. Okay, that at least gives you the exact p-value, which is nice because when you make your decision, you can say, since the p-value of 0.0703 is greater than the alpha level of 0.05, we fail to reject the null hypothesis. And then we go on and make our concluding statement that we then do not have convincing evidence that the company's stated color distribution is not correct. Okay, please note, what I listed here is that I didn't have evidence, and then after the word that, I was basically listing what my alternative hypothesis is. I didn't have evidence that, and I stated the alternative hypothesis. Okay, what you'll notice is at the bottom of this page is just what your calculator screen should look like when you're selecting that chi-squared CDF feature. Okay, we're going to end today with one final example here, walking through this example that's talking about birthdays and National Hockey League players. It says, in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, because January 1st is the cutoff date for youth leagues in Canada. Canada is actually where there are a lot of the National Hockey League players sort of come from Canada. Players who were born in January will be competing against players who could be up to almost 12 months younger than them. The older players tend to be bigger, stronger, more coordinated, hence they get more playing time, more coaching, and have a better chance of being successful. Okay, you'll notice I listed here our formula for how to calculate the chi-square test statistic. We want to see if a player's birth date is related to their success, judged by whether they make it into the NHL. Okay, so a random sample of 80, we have 80 in our sample, National Hockey League players from a recent season was selected, and they were asked what their birthday was. We want to see if their birthday was close to January or not. Okay, there are a total of, we're going to need this number later here, there's a total of 879 National Hockey League players. Okay, so here you can see that we have whether their birthday fell between January and March, April and June, etc. These are the 80 NHL players. Okay, so this total is 80, and you can see the counts that fell in between. This is what was observed. Okay, the question is, do the data provide convincing evidence, that's our phrase that means we're supposed to run a significance test here, that the birthdays of National Hockey League players are not uniformly distributed throughout the year? Okay, so we're expecting maybe this is skewed a little bit because those stronger players that actually made it to the NHL have that earlier birth date there. So I want to introduce you to what the conditions are for performing a chi-square test for goodness of fit. We skipped this in the last example. Okay, as you probably anticipated, we have to make sure that our sample is random, or if it's an experiment, that the treatments are randomly assigned. As you are used to checking, we need to do that 10% condition. Often we write it like this: 10 times the sample size is less than or equal to the population size. And then here's the new part, the large counts condition. We need to show that all of the expected counts are at least 5. Okay, that's a new number there, at least 5. And please draw your attention to the fact that we should never be rounding these expected counts. Okay, you have to make sure that you are checking the expected counts, not the observed counts. Okay, and once again, this is not a check for normality. In fact, we said earlier that the chi-squared distribution is always skewed to the right. It is not normal. Okay, so one of the things you may want to do at the beginning before you even start running through the Phantoms acronym here is to go ahead and list what your observed counts are and what your expected counts are. You're going to need to have calculated these anyhow. Well, the observed counts, we can just pull those right from the table above. Now, we are expecting that the birthdays of these National Hockey League players, that it's just evenly distributed throughout all 4 quarters of the year. And maybe I should list what our hypothesis is first here. Okay, we skipped the P for parameter. Our null hypothesis is that the birthdays of National Hockey League players are just evenly distributed throughout the 4 quarters of a year. Okay, that's kind of how they chunked the birthdays up here into each of the 4 quarters. And so we're saying, look, it doesn't really matter when your birthday is. There's sort of an even number of National Hockey League players from each of those 4 quarters. And so if our sample size is 80, then what I would expect is I would expect 25% to be from January through March birthdays, 25% April through June, etc. So I would expect 20 of each of the 80 to fall in each of those different quarters of the year. And of course, our alternative hypothesis would be that the birthdays of National Hockey League players are not evenly distributed throughout the 4 quarters of a year. Okay, and you'll notice I already have listed here that we're going to use an alpha level of 0.05. Okay, we are now going to go ahead, Alexa, stop. We are now going to go ahead and run through our list of assumptions. These are our 3 conditions. We need to make sure that we have made some statement here that a random sample of 80 players was taken. Okay, we're going to show the 10% condition, and this is why they told us in the problem that the National Hockey League consists of 879 players. That was listed there for our benefit, so when we do the 10% condition and we multiply our sample size by 10, we make sure that that is still less than or equal to the total number of National Hockey League players, which it is. Okay, that's less than the 279 NHL players. Okay, and then finally, we're going to do our large counts condition, which is not for normality, okay, but it is checking these expected counts have to all be greater than or equal to 5. Now, you can see as long as you've shown the graders what your expected counts are here, you can simply make a statement that all expected counts, which are 20 in this case, are greater than or equal to 5. Okay, the name of our test is the chi-square, I'm going to abbreviate here, GOF, for goodness of fit test. And then we're going to go ahead and proceed, and we're going to calculate what the value of the chi-squared test statistic is. Okay, so we're going to go ahead and do observed minus expected squared over expected. Okay, we're going to do this for all 4 of the quarters. Observed minus expected squared over expected. Okay, when we do that, we get a chi-squared test statistic of 11.2. I would encourage you, when you are finding the p-value, to go ahead and just use chi-square CDF. You do, again, always have to label your calculator inputs, lower bound, upper bound, degrees of freedom. Okay, lower bound is that chi-square test statistic. Upper bound is the 10,000. Degrees of freedom on this, we have 4 categories. The 4 categories are the 4 quarters. We subtract 1 from that, our degrees of freedom should be 3. This is going to give us a p-value of 0.011. Okay, our decision on this will be, since the p-value of 0.011 is less than an alpha level of 0.05, in this scenario, we would choose then to reject the null hypothesis and say that we have convincing evidence that, okay, and after the word that, this is where you're going to list what your alternative hypothesis is. And that is that the birthdays of NHL players are not evenly distributed through the 4 quarters. Okay. I will be showing you in the next video how to use a chi-square goodness of fit test on the calculator. It is important, though, that on these problems that I'm asking you to do here, that you go ahead and use the formula observed minus expected squared divided by expected to come up with the value of your chi-squared test statistic.